we have
Force,
to apply concept of vectors, sir.
force is given in vector form. Displacement also given in vector form. We are asked to find out work done. We know work is F dot S. F dot S. So F is 3I minus 2J plus 4K dot 2I plus J minus 3K. If you remember dot product, this is a oral question. If you remember and understand how we did the dot product, this is a oral question. Without using pen and paper, you can tell the answer. So dot product, I dot I, 3 into 2,
Sir,
6
6 I
minus 2 plus 1,
minus 2G.
minus 2 plus 4 into minus 3,
minus 12.
minus 2. So this is
Sir, minus
minus
8.
14 plus 6 minus 8, minus 8 joule. Work done is minus means what does negative sign indicate? That force and displacement are opposite in direction. Negative sign indicates force and displacement are opposite in direction. And again, they need not be exactly opposite. Theta is lying in second quadrant. Theta is lying in second quadrant. Okay. Then next, suppose this is the question. A body is displaced from RA. R means position vector. 2I plus 4j minus 6k to RB 6I minus 4j plus 2k. Under a constant force F equal to 2I plus 3j
Sir,
minus.
can we do this question, sir?
Yes. Find the work done. You are given force in vector form, and you are given position
Initial and final position.
RA, RB, initial and final positions. From that, how to calculate work done?
Sir, first we have to subtract the RB point minus RA point, sir, to find the displacement.
Hmm.
Next we can multiply, sir, dot product.
Hmm.
We'll find the works.
Let's do it.
Sir, I got minus 12 joules, sir.
Minus 12. See. So R a position vector of point A. Let us say this is some point A. Position vector of this A is given. This point is given. That means with respect to some origin. With respect to this is a actually this is XYZ vector. This is x-axis, y-axis, z-axis. This is the origin, and point A is somewhere here. Its position vector is this, which is RA. Okay, and point B, let us say it is somewhere here. Its position vector is this, which is RB. Okay. Now a body moves from point displaced from A to B. Body is displaced from A to B. The body was here, it went here due to the force F. So this
Equals
is
to vector RB minus RA.
displacement. Displacement is final position minus initial position. Displacement is final position minus
It's
initial.
just a triangle law, right?
You should not do RA minus RB. RA minus RB is different, RB minus RA is different. Displacement by its definition is final position minus initial position. So RB minus RA. RB minus RA, how much is it? 6i minus 2i, 4i, minus 4j, minus 4j,
Minus 8J.
minus 8, plus 2k,
Plus
minus
8K.
6k,
So
minus
plus
4,
8K.
minus no, minus of minus plus. So 2k minus of minus 6k plus 8k. This is the displacement. Force is there. 6i minus 4j plus 2k. So work done. F dot S. Same dot product.
Sir, 8, sir.
6 into 4, 24.
Sir, minus 32.
Minus 4 into minus 8 plus 32
Plus 32. Plus 16.
plus 2 plus 8 plus 16. So 32, 16,
72.
24, 16, 40, 72. 72 joule is the work done.
Sir?
Hmm.
Sir, so for this, you should use the triangle law, right?
You can also say it is triangle of vector addition.
Okay, sir.
And this direction will be this.
Sir, I did not understand
Oh,
why shouldn't we take the force as 2i plus 3j minus k, sir?
oh sorry, sorry. I looked at this. Force is wrong. So force is not 6i, no, it is 2i.
Yes, sir.
Force is 2i plus 3j minus k. Okay. Now multiplying 2 force 8, 3 minus 8, minus 24, minus 1 into 8, minus 8. 8, 8 gone,
Minus 24.
minus 24 joule. Yes, this is correct. Minus 24 joule. Next. Do this.
Sir, 36, sir, I got. 36 June.
Hmm.
Sir, I also got 36, sir.
Hmm.
Where to do trapezium area formula, sir?
Hmm. So graph is given, force displacement graph. From that work is area under the graph. If you apply formula for trapezium, it is half into a plus b into h. So half into a plus b. A, this is a, this is b. A is how much?
The 4.
A is 10 minus 6, 4. B is 14. Height is 4. 2 ones, 2 twos, 14 plus 4, 18. 18 into 2, 36. Joule is the answer. Okay. Next. Hmm. A force of 1200 Newton acting on a stone by means of a rope slides the stone through distance 10 meter in a direction inclined at 60 degree to the force. Work done by the forces. So if you understand the situation clearly and make a picture of it, this is a surface, horizontal surface. This is a stone. This is a stone. To this stone, a rope is tied
Sir,
and it is pulled. How? In a direction inclined at 60 degree to the force. That means I am applying a force like this.
sir, I got 6,000 joule.
Wait, let us see. This is 1200 Newton force. Let us say with respect to horizontal, this angle is 60 degree. So the stone is sliding in this direction. Then what is the work done? It is sliding up to 10 meter.
Sir, I got
Displacement
6000 root 3 joules, sir.
6000 root 2. See, now the point here is you can apply Fs cos theta. W is equal to Fs cos theta. F 1200. Displacement 10.
Sir, 1 by 2.
Cos 60. Cos 60. So 1200 into 10
Sir, into 1 by 2.
into 1 by 2. 2 ones, 2 5s. 6,000. 6,000 joule. Next. A man weighing 80 kg climbs a staircase carrying 20 kg load. Staircase has 40 steps, each of 25 centimeter height. If he takes 20 seconds to climb, the work done is. So what is the situation? There is a staircase like this. Height of each step is 25 centimeter. This height 25 centimeter. Okay. And there are 40 steps.
I got 98.
A man has to, he is carrying a load of 20 kg and his mass is 80 kg.
Sir,
If he
9,000.
climbs up the staircase, what is the work done? See, work done. What is work done? Force into displacement. Force into displacement.
Sir, it is mgh here.
What is the force applied here? Work
Sir,
done, first of all, work done by whom is to be calculated? Work done by man. Work done by man is to be calculated. So force applied by man into displacement of man. Okay. What is the force applied by man? In order to climb the stairs, first of all, he has to lift his own weight. And he is also carrying another additional weight. So he has to lift that weight also. Right? This is the force into displacement, which is height to which he is climbing. Okay. So this can be written as m plus m g into h. Okay. What is h here?
Sir, 10, sir.
Substitute the values. This is 80. This is 20 into.
9.8.
I should take 9.8 because by looking at the options, you should get the idea. They are not round figures. So I should take g as 9.8. Or even if you take 10, You'll get nearest value. You can put that to reduce calculations. I'll take 10. Then we'll see which where
Sir,
option
how
will be
height
close.
equals to GH, sir?
Huh?
We are taking G common, sir.
J common.
Okay.
Sir, into 10, sir.
Height.
10.
So height is what height of each step, which is 0.25 meter into 40 steps. This is the total height to which he is climbing. So this is 100 into 10 into 45, 40 into
Sir,
this
10.
10. So 1000, 10,000, 10,000 joule. If you take G as 9.8, you'll get 9,800. 9,800 joule.
Sir, 20 seconds is unnecessary here, sir.
Is not required here. So
Sir, 20
sometimes
seconds is required for
information
power,
might be
right?
given which is not required by us. You should ignore it.
Sir, 20 seconds is required for power, right?
Yes.
Rate of change of.
Okay, right. This is work. Next, energy. Next concept, energy. Energy is also a commonly used term which we use in our day-to-day life. You use this energy in not only in physics. You come across this energy in chemistry. You get this in biology also, right? So energy, we need energy to survive. We need energy to do work. You need energy to play. You need energy to go to school. Okay, and greater the energy you have, stronger you will be. In such context, we will be using energy. In physics, how did we define this energy? Energy is described as it is the capacity of a body to do work. Capacity of a body to do work is energy. You get your energy from your food that you eat to do your day-to-day activities. To walk, to run, to read, to go to school. You need energy. From where do you get that energy? From the food that you take. So that's why your parents always insist you to take good nutritious food. Okay. So that from the food that you take, you might have studied in biology, your digestive process in digestive system, this um, food will be broken down and it will be converted into chemical energy. This chemical energy will be stored in our cells, mitochondria. Mitochondria are the powerhouses of the cells, right? And that stored chemical energy will be converted into mechanical energy or muscular energy through which we do work. So this energy, we find this energy in different forms in nature, like how you find matter in 3 4 different forms: solid, liquid, gas, plasma. Similarly, energy is found in nature in various forms. Energy is found in various forms, like various forms of energy are um, chemical energy, mechanical energy,
Sir, solar energy.
uh, solar or right, light energy,
Sir, sound energy.
sound energy. Sound is also a form of energy. Heat energy. Then you have nuclear energy, You have geothermal energy, electrical energy, magnetic energy. Various forms of energies are there in the nature. But now in this chapter, in this particular chapter, work energy power, we will be considering only this type of energy, mechanical energy. Mechanical energy. So mechanical energy is that energy which is possessed by bodies either due to their motion or due to their position. Because that type of energy is mechanical energy. Or the energy due to which bodies can do work is mechanical energy. Mechanics means motion. That's how it is. So we'll be studying about mechanical energy in this chapter. Right. If you take mechanical energy, mechanical energy. See, why are we describing energy in terms of work? Energy and work, they are directly related to each other because greater the energy you have, greater the work you can do. Just simple logic. Okay, suppose if you are fit and fine, you can walk, you can jog, you can run, you can play, you can do all activities. But suppose you have got fever, you are ill, you cannot do all your day-to-day activities as usual because when you are ill, your energy levels go down. So if you don't have energy, you cannot run, you cannot play, you cannot do these regular activities. Okay, so in that sense, energy and work are directly related. If a body has more energy, it can do more work. If a body has less energy, it can do less work. If a body does not have any energy, it cannot do any work. That's why energy and work are directly related. Capacity to do work is energy. A, a person can run 1 kilometer. Another person can run 2 kilometers. Who has more energy? One who runs for 2 kilometers has more energy because he is able to do more work. He is applying effort, he is putting some force and is getting displaced. So he is doing work and he is doing greater work. So he has got greater, more energy. Okay.
Sir,
Hmm.
sir, is work is equals to K into energy or energy is equals to K into work or both are equal, sir?
The exact relation between work and energy will come across that. We have something called work energy theorem, which gives us the relation between work and energy.
Okay, sir.
Right. So this mechanical energy is of two types. One is kinetic energy. Second is potential energy. Kinetic energy and potential energy. What are these two types? Kinetic. Kinetic means motion. Anything which is moving, we call it as kinetic. Right. So the energy possessed by a body due to its motion is kinetic energy. Energy possessed by a body due to its motion is kinetic energy. K in short. Okay. Suppose we have a body of mass m which is moving with a speed v. Then this body has energy. How much energy? Kinetic energy due to its motion, which is equal to half mv square. Very, very important and regularly used formula in physics. Kinetic energy of a body is half mv square. What is m? Mass of the body. What is v? Speed of the body. Speed or velocity, whatever. Half mv square is the kinetic energy of the body. Okay. If v is 0, speed is 0, that means the body is at rest. Body is at rest, kinetic energy is 0. So bodies possess kinetic energy only as long as they are moving. If bodies are at rest, then there is no kinetic energy associated with them. If a body is at rest, then K equal to 0.
Sir,
Uh,
sir, this formula is applicable only when U is 0, right?
even U is there or U is 0, it will have kinetic energy. If it starts from this and it is moving, it will have kinetic energy. If it is already moving and it continues to move, it will have kinetic energy.
Okay, sir.
Again, what is the unit in which we measure kinetic energy? Kinetic energy is also energy, so it is also measured in joule. Kinetic energy is also energy, so it is measured in joule.
Sir,
Okay.
what is the formula if U is not 0, sir?
Same thing, half mv square.
Sir, then won't we get different results, sir?
If the speed of the body is changing, its kinetic energy will also change.
Okay, sir. Instantaneous, sir.
Uh,
Okay, sir.
Mass, however, will be constant. If a body is moving with constant speed, it will have constant kinetic energy. If it's moving with variable speed, increasing or decreasing, its kinetic energy will also change. To calculate that instantaneous kinetic energy, you have to take help of calculus, integration. Right. Kinetic energy. And some examples of some bodies which have kinetic energy. Suppose you fire a bullet from a gun, that bullet has kinetic energy. You fire an arrow, that arrow has kinetic energy. If you hit a ball with a bat, cricket ball with a bat, that ball has kinetic energy. If you are running, you have kinetic energy. A moving car has kinetic energy. A flying aeroplane has kinetic energy. Anything which is in motion will have kinetic energy. Next. And one more thing, one more important relation here, which is relation between kinetic energy and momentum. We already know what is momentum. What is momentum?
So the product of mass and velocity.
Product of mass and velocity. So momentum is mass into velocity. Now, if I take this formula for kinetic energy, which is um, half mv square or mv square by 2, I will multiply and divide this with m. So it becomes m square v square by 2m.
So equals to P square
If
by 2.
mv square by 2m. mv is momentum square by 2m. So kinetic energy is p square by 2m. P is momentum. P square by 2m. Or from this you can also write P is equal to root of 2m k. If you are given kinetic energy mass, you can calculate momentum. If you are given momentum mass, you can calculate kinetic energy. Okay. Suppose a car and a truck both are traveling with same momentum. Which has more kinetic energy? Car and truck are traveling with same momentum, which has more kinetic energy.
Sir, car, sir.
Car, how?
Sir, because the mass is lesser in car than in the truck, sir.
Hmm. In K equal to P square by 2m, P is constant here. P is same for both. That means K is proportional to 1 by m. Lesser the mass, greater the kinetic energy. Mass of car is less than mass of truck. So car has more kinetic energy
Sir, if momentum is same, sir.
if momentum is same. Car and a truck both are traveling with same kinetic energy. Then which has more momentum?
Sir, truck, sir.
Truck. K equal to P square by 2m. What is constant here? K is constant. That means P square is proportional to m, or P is proportional to root m. So greater the mass, greater the momentum. Truck has more mass, so truck will have more momentum. Truck has more momentum. Okay, right. This is kinetic energy. This is kinetic energy. Next, coming to potential energy. Potential energy. Potential energy can be possessed by a body in three different ways. What are they? We call them as a body can have potential energy in three ways. They are: first is gravitational potential energy. Gravitational potential energy. Second is elastic potential energy. Third is electrostatic potential energy. Gravitational, elastic, electrostatic. What is the relation, or how do we understand these different things? Simple. Gravitational potential energy is the energy possessed by a body due to its position. Due to the position. If a body is present on the surface of Earth, another body is present at a height of 10 meters, another body is present at a height of 100 meters. So with respect to position of the body, depending on the position of the body with respect to surface of Earth, bodies can have gravitational potential energy. How we will come to that? This second is elastic potential energy. This elastic potential energy is uh, mm, okay. Maybe let us take gravitational further. Suppose this is the surface of Earth. A body of mass m is present on the surface, and another body of same mass m is at a height h above the surface of Earth. Is at a height h above the surface of Earth. Okay. Now this body, which is at a height h, will have potential energy due to its position. How much energy? See, how did that body go to height h? Someone should have lifted it. Someone should have, you have lifted it. Suppose there is a book lying on the floor. You lift that book and you are holding it, let us say, at the level of your head. Okay. To lift that book from ground to height h, you applied force. You applied force and there is displacement. That means you did work. You did work. How much work is done by you? Force into displacement.
Sir,
How
mgh.
much is force? The minimum force that you need to apply to lift that book is equal to its weight, and displacement is h. So W is equal to mgh. This much work is done. Where will this work go? You have done work means you have spent energy, because energy is the capacity of a body to do work. If you have done this much work, mgh amount of work, then your energy has decreased by mgh, right? Your energy has decreased by mgh, because if you imagine you do this 1,000 times or 10,000 times, place a book on ground, lift it to height h, place it again on ground, lift it to height h. If you go on doing this 10,000 times, you'll get tired and you will fall down. But if you just do it once, you'll not feel any difference in your energy level. Still, there is energy which is being spent by you. So if you are spending energy, where did that energy go? Energy cannot disappear in nature. Energy is conserved in nature. Energy is conserved, just like how mass and charge are conserved, energy is also conserved. So the energy which you have lost is transformed into some other form. What is that some other form? That energy is now stored in the book in the form of potential energy. Potential energy. So this amount of work that you do is converted into potential energy, and that potential energy is now mgh. That potential energy is mgh. So a
Sir,
job
is only case of gravitational force, sir.
only due to gravitational force. You get bodies get potential energy, gravitational potential energy, only due to gravitational force.
Okay, sir.
So this is how bodies get gravitational potential energy. And the general formula to calculate gravitational potential energy is mgh. Many students remember like potential energy is mgh, potential energy is mgh. Not all potential energies are mgh. Only gravitational potential energy is mgh. Okay, fine. Second type of energy, elastic potential energy. Elastic potential energy. Bodies possess this potential energy due to change in configuration, configuration or arrangement of a system. So there is some system present. If you change its configuration, alignment, or arrangement, something, then to change that configuration, you should have done some work. That work will be stored in the body or in the system as elastic potential energy. How? Simple example. Let us take a spring. This is a spring of constant k. We have discussed what is a spring constant. Now, if I stretch this spring, if I elongate this spring, to elongate the spring, I should apply force. Suppose I have applied force in this direction, and its elongation is some x. Then I am doing work. I am doing work on the spring. Okay. Force F is applied, displacement is x. So work is done on the spring. I am doing work. I am doing work means I am spending energy. Again, where is this energy going? My energy, let us say, I have done 10 joule of work. That means I have lost 10 joule of energy. Where did this 10 joule of energy go? This 10 joule of energy went into the spring. Now the spring has got potential energy because you changed the arrangement or configuration of the spring by doing work on it. The work that you did will be stored in the spring as its potential energy. The same thing happens if you compress it. Same thing happens if you compress it. Okay, or you can take another example, let us say, of a bow and arrow. This is a bow. Okay, if you want to shoot an arrow, what you do? You put the arrow and you pull the string back like this. you are pulling the string back. If you are pulling the string back means you are applying force on it. You are applying force, there is displacement of the string. So that means work is done. Work is done means you are spending energy. Where did the energy go? This energy is now stored in the string as its potential energy. Okay. So all these things we call them as the all these energies possessed by bodies due to this change in their configuration. We call them as elastic potential energy. And how much will be this elastic potential energy depends on the situation. For example, if you take for a spring, its potential energy will be half kx square. K is spring constant and x is displacement of the spring, elongation or compression. Potential energy stored in a stretched spring is half kx square. This is what is this? Elastic potential energy. Third one,
Sir, I did not understand derivation of the formula, sir.
which formula? We are not deriving any formula. I'm just giving directly formula. We don't need the derivation right now because that involves integration, all those things. We are not going to the derivation of potential energy of a stretched spring. I'm directly giving the formula half kx square.
Okay, sir.
Third one is electrostatic potential energy. Electrostatic potential energy is due to the charges. Electrostatic charges due to charged bodies. Charged bodies. Okay. Suppose you have two bodies which are charged. Q1, Q2 are the charges. Let us say positive charge, positive charge. There will be repulsion. If there are opposite charges, plus Q1 minus Q2, there will be attraction. So when you arrange charged particles in one particular configuration, you will be doing work on that system. That work done will be stored as electrostatic potential energy. So electrostatic potential energy will be possessed by bodies, only by those bodies which have charge. And you get to study this thing in detail in your class 12, where you study about charges. So we'll not go into further details. This is just for idea for you that potential energy can be possessed by a body in three different ways, either due to gravitational force or elastic forces or electrostatic forces. In this chapter, again, we will be discussing mostly about gravitational potential energy, for which a general formula is mgh. This is energy, mechanical energy, two types of mechanical energy, two types of mechanical energies, which are kinetic and potential. What is kinetic? How does a body get kinetic? The relation between kinetic and momentum. Then potential energy types. How much will be gravitational potential energy? Okay, this is about energy. Next is we should discuss work energy theorem, which is very important. But we'll take a small break for 3 minutes. Break for 3 minutes. Meanwhile, if you have any questions, you can ask. I hope all of these your final examinations are in April, right? Or they are in.
Mine is done, sir.
Okay. If your exams are done, what's going on for you in school?
Sir?
Are your exams over? Final exams?
Yes, sir.
Okay. What's going on then?
No, sir.
Sir, yesterday only done, sir.
Okay.
Sorry, sir. Today, sir.
Oh. So whatever, what all we have been learning right from the starting of our classes, you should be continuously revising them. If you just throw your books away, you'll forget. Forgetting is very easy. Forgetting is a gift given by nature to man. We tend to forget everything, even if it is if something very bad or something very good. Our human nature is to forget everything, but we cannot do that in case of studies in academics. Okay, because every every academic year will be based on the previous academic year. What you learned in class 8 will be carried forward in class 9. So if you go to class 9 with a empty mind, you don't understand much. And if you enter into class 10 with empty mind, without by forgetting all what you have learned in class 9, you don't understand much. It will be difficult for you. So you should carry at least the fundamentals, at least the basics of your previous academic year. And that's how our education system is designed. All these things that you are studying now in your class 9 or in our this course, foundation course, these will be carried forward in class 11 and 12. So if you have clarity on these concepts and enter into class level, then you will be ahead of your other competitors. You will get a edge over your other competitors. So you have fair chances of getting good marks or getting good ranks in competitive examinations. Right. Let us get back. Right. See, work energy theorem. Work energy theorem. Very important concept in physics. What is this? As the name says, it gives us the relation between work and energy. What is the actual relationship between work and energy? Let us take a body of mass m. Okay, which is moving with some initial velocity u. It covers a displacement s, and say its velocity becomes v here. Its velocity is changing. That means velocity changing means there is acceleration. If there is acceleration, there will be force. There is force, there is displacement. That means work is being done on this body. Work is being done. How much is the work? Work equal to force into displacement. Okay. Force into displacement. Force is mass into acceleration into displacement. I can write acceleration as v square minus u square by 2s. Second kinematic equation into s. S cancelled. So work is equal to m into v square minus u square by 2, or m v square minus m u square by 2, distributing the splitting the denominator, m v square by 2 minus m u square by 2. What is m v square by 2? Half m v square, kinetic energy. Which kinetic energy? Final kinetic energy. Minus m u square by 2. U is initial velocity. So m square bit is initial kinetic energy. Ke initial. And what is final kinetic energy minus initial kinetic energy? It is the change in kinetic energy. It is the change in kinetic energy. Okay. So finally, what can we say? Work done on a body is equal to change in its kinetic energy. This is the relation between work and energy, and we call this as work energy theorem. Work done on a body is equal to change in its kinetic energy. Right? Simple thing. Suppose if you have a question like this. mm, this one. A body of mass 2 kg is projected with initial velocity 5 meter per second along a rough horizontal table. Work done on the body by the friction force before it is brought to rest is. So see, understand this. We have to calculate work done here. We should find work done. Normally, what formula do we have to calculate work done? Force into displacement. Okay, fine. Is force given in the question? No, you don't find any force. Only friction force is mentioned, but its value is not given. Okay, so force is not given in the question. Is displacement given? No, displacement is also not given. Mass is given, velocity is given. Displacement. Force is not given, displacement is not given, but you are asked to find work done. Then immediately you should get an idea that you cannot use this formula here. Force into displacement is not useful. Then you should go for work energy theorem. We have another formula to calculate work, which is change in kinetic energy. Can we apply it here? Yes. This is a horizontal table. This is a rough horizontal table. That means friction is there. On this table, you are projecting a body. This is 2 kg mass with initial velocity 5 meter per second. Because of friction, what happens to this? It stops. It stops after traveling certain distance. We don't know that distance. We don't need that also. Finally, it is stopping means its final velocity is 0. Okay. What is work done? Change in kinetic energy. What is kinetic energy? Final kinetic energy minus initial kinetic energy. How much is final kinetic energy? 0, because it is stopping. Minus how much is initial kinetic energy? Half mu square, which is 0 minus half into 2 into 5 square 25. 2 gone. W is equal to minus 5 joule. That's all. Work done is minus 25 joule. Work energy theorem. So remember this point. If you don't see force and displacement in question, but still you want to calculate work done, you should think of work energy theorem. Right. Next. And say this is the derivation of work, not derivation. This is a what you call okay, derivation of work energy theorem. You start with W is equal to Fs, write F as Ma, write A as V square minus V square by 2s, cancel this thing, you'll get this thing. this derivation, statement of work energy theorem, and this derivation. This is a very, very important 8-mark question for your intermediate first year public examination. 8 marks question. For this small thing, you'll get 8 marks. So if you understand and if you can do this, that means there are chances that you can easily score 8 marks in your physics public examination of intermediate first year.
Sir, for the derivations,
Yes, you should write the statement of, actually it will be asked like, define work and energy. So you should write definitions of work and energy. Then give the statement of work energy theorem, work done is equal to change in kinetic energy, and derive this relation. That's all.
okay.
Next thing, law of conservation of energy. Another very important concept. Law of conservation of mechanical energy. What does this law say? Simple. The total energy of a body is conserved, or in another way, and other words, energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed, but can be converted from one form to another. The same applies to mass also, and the same applies to charge also. Mass can neither be created nor be destroyed, but can be converted from one state to another state. Charge can neither be created nor be destroyed, but can be transferred from one body to another body. This is law of conservation of energy. Okay. The total, see, there are only these two things in the universe, right? Matter and energy. Matter, you cannot create matter, you cannot destroy matter. Whatever matter is there, right from the creation of universe, the same thing is running until now, and it will keep existing. And the same is with energy. The energy that was present at the time when this universe was created, the same energy is present even today. No addition, no subtraction. Okay. But you can convert energy from one form to another form. That is allowed. You can convert mechanical energy to electrical energy. You can convert electrical energy to light energy. You can convert light energy to electrical energy. Different conversions are possible. But total will remain same. And we can verify this thing in a simple situation. Verification of law of conservation of energy, particularly mechanical energy. What is it? Let us say we have a body of mass m, let us say a ball of mass m, which is released from point A. This is point A. And point A is at a height of capital H from ground. Okay. If you it is released from rest, that means initial velocity is 0. If you release it, what happens? It falls down. Okay, while it is falling down, let us take its position somewhere here during its journey. Let us say this is point B. And how is this point B? Point B is at a height small h. from point A. Okay, right. Then just before it strikes the ground, this is point C. Okay. Now, if I write the total energy of the body at points A, B, and C, total energy of the body at points A, B, and C. What is total energy of a body? A body can have mechanical energy in two ways. One by kinetic, other is by potential, gravitational potential, right? And the total mechanical energy will be the sum of these two things. Total mechanical energy will be the sum of kinetic and potential energies. I will write that point here. Where total energy is kinetic energy plus potential energy. Okay. Suppose you have a car which is running on a straight road. What energy does that car has?
Kinetic energy.
Kinetic or potential or both?
Sir, both, sir.
How can it has potential energy?
Sir, zero, sir.
It has only kinetic energy. Suppose the aeroplane is flying horizontally. Due to its speed, it has kinetic energy. Due to its height, it has potential energy. So a flying aeroplane, a flying bird, anything which is moving at a certain height will have both kinetic and potential energies. Then the total energy of that aeroplane will be the sum of its kinetic and potential energies. Right. So simply if you add kinetic and potential energies of a body, you will get its total energy. Now, see here. We are dropping a body from point A, which is at a height capital H from ground. At that point, at point A, what is the kinetic energy of the body? Zero, because you are releasing it from rest. Okay, what is potential energy of the body? It is at a height capital H from ground. So it has potential energy mg capital H. Okay. Then what is its total energy? Ke plus Pe,
Sir, equals to P, sir.
which is 0 plus mgh, which is mgh. Okay. So at point A, the total energy of the body is mg capital H. Okay, fine. If I do the same thing for point B, where is point B? At a height small h below point A. Right. At point B, does the body has kinetic energy? Yes, it will have, because it is falling down. While falling down, it will have some velocity here. Let us say that velocity is some VB, velocity at point B. Okay. So potential kinetic energy of the body is half m VB square, velocity at point B. And how much will be velocity at point B? I will apply second kinematic equation to find that V square equal to U square plus 2GH. U is 0. Okay, U is 0. So V square can be written as 2G small h, right? Do you follow this? Two cancelled. What is this? Mg small h. Okay, this is kinetic energy. What about potential energy at point B? Potential energy is mg into height. mg into height. Height from where? From point A or from ground? With respect to ground. So what is the height of the body at point B? Where from ground? Is it capital H minus small h? Yes. So that means it is mg capital H minus mg small h. Okay. Then what is total energy? What is the total energy? Ke plus P. Ke mg small h. P mg capital H minus mg small h. These two cancel, which is again mg capital H. So what is total energy at point B? mg capital H. Okay. Do the same thing at point C.
Sir,
Hmm.
Sir, how is VB square 2GH, sir? Could you tell again?
V square equal to U square plus 2GH. Second kinematic equation. What is U? We are applying this between points A and B. Initial velocity is 0. U is 0. So V square is 2GH, height by which it falls, small h.
Okay.
Next, at for point C, for point C, what is kinetic energy at point C? Will the body have kinetic energy at point C? Yes, because while it is falling down, its velocity will be maximum just before striking the ground. Let us say that velocity is some Vc, velocity of striking. How can we write, what is the kinetic energy here? Half mvc square, which is equal to half m. Same thing. I'll do the same thing. If I apply v square equal to u square plus 2gh between points A and C, I will get vc square as 2g capital H. So 2 cancelled. This is m capital H. Okay. What is potential energy at point C? Point C is ground. Height is 0. Height is 0. Potential energy is 0. So what is total energy? K plus P. 0 plus mgh. mg capital H. So total energy is mg capital H. Now what do you say from this?
It is conserved in a body, sir.
Hmm. Total energy at point A is mgh. Total energy at point B is mgh. Total energy at point C is also mgh. That means total energy of the body is remaining constant. Remaining constant means it is conserved. It's not changing. Okay. But kinetic and potential energies are changing. At point A, kinetic energy was 0. Potential energy was maximum. At point C, kinetic energy is maximum. Potential energy is 0. So the kinetic energy at point A, sorry, the potential energy at point A is converted into kinetic energy at point C. Kinetic energy is increasing, potential energy is decreasing. He is increasing. As the body falls down, kinetic energy increases. Energy is increasing. From where is this energy coming? Energy cannot be created. So it is derived from the potential energy of the body, which is decreasing. If one energy increases, the other energy will decrease so that the sum remains constant. This is what law of conservation of energy says. Okay. And this is another 8 mark question from this chapter. There are very high chances that you will get either one of them for your board examination. Simply this derivation, that's all. Statement, derivation. Of course, you have to explain it in detail while writing. That's a different thing. Right? Law of conservation of energy. Next, last part, power. Power. Power is also a commonly used word, right? Tell me one example where you use power in day-to-day life.
Sir, in bulb.
Bulbs. Okay. And
Sir, strength.
in describing or in expressing strength of a body, we use power in the
That comes like mostly in electricity bill.
Sir, electricity.
yes.
Electricity.
Right. Electricity also we define power. You in we call electricity itself as power. There is power cut. You call it like that. Okay. In terms of mechanics, in the context of this work energy power, we define power as the rate of doing work. It is the rate of doing work. The rate at which a body can do work is its power. Rate means with respect to time. In unit time, how much work can be done by a body. That will be its power. Okay. So power is work done by time. And the standard symbols that we use: power capital P, work W, time T. Power is work by time. Then what is the SI unit of power? Work by time. Work is measured in joule, time is measured in second, so it should be joule per second. But we have given a special name to this unit, which is watt, WATT, after the famous scientist James Watt. What did James Watt invent? What did James Watt invent? Steam engine. James Watt invented steam engine. So, in memory of that famous scientist, we have named the unit of power as watt, and its symbol is W, capital W. So, don't get confused with W of work and this watt, W of watt. Depending on the situation, you should understand which W is what. Okay, SI unit is this. Then, what is its nature? It is a scalar quantity. Power is a scalar quantity. No direction. Then, in addition to watt, another practical unit of power is horsepower, HP. HP. How much is 1 HP? 1 HP is equal to 746 watt. You will be using this HP to describe the power of motors particularly. If you have motor at your home, which is used to pump water, then if you ask your parents, they'll tell you what is the power rating of the motor that you have at your home. It might be half HP motor, 1 HP or 2 HP motor, depending on how high your overhead tank is. Okay. So 1 HP motor means its power rating is 746 watt, right? And if you want to get more clarity on this, see, when do you say that the power of a body is 1 watt? When it can do 1 joule of work in 1 second. If a body can do 1 joule of work in 1 second time, then its power is 1 watt. If it can do 10 joule of work in 1 second time, its power is 10 watt. Okay. If you compare this with this HP, so if a water pump has 1 HP power, that means it can do 746 joule of work in 1 second time. Then its power is 1 HP. Okay, right. Or in the context of these bulbs, electric bulb, if you purchase a bulb, you should ask for the power rating. If you go to the electrical shop and ask for a bulb, they'll ask you what power do you want? 40 watt, 60 watt, 100 watt, or for LED bulbs, it will be 14 watt, 16 watt, 9 watt. Different categories of bulbs will be there. Suppose you are purchasing a 60 watt bulb, 60 watt electric bulb. Okay. That means if you are using that bulb, then that bulb will consume 60 joule of energy every second. That bulb will consume 60 joule of energy every second. What energy is it consuming? Electrical energy. The bulb will consume 60 joule of electrical energy every second. Then its power rating is 60 watt. If you are purchasing a 9 watt bulb, it will be taking only 9 joule of energy in 1 second. That's what we mean by power rating. Okay. Now, if you come to mechanical power, if you take it in different situations, for example, let us take a simple question. Okay. A man of mass 60 kg can climb to height 12 meter in 1 minute. Let us say he's climbing a tree or he's climbing over a rope, something. Find his power. Find his power. How to do this? What is power? Power is work by time. What work is he doing? He is climbing to a height. That means work done is mgh. Okay, or work done is force into displacement by time. What is force? Mg. He is lifting his own weight to some height h, divided by mass is 60, g is 10, height is 12, time is 1 minute. Should I write 1 here? No, seconds. 60. 60 gone 10 into 12, 120 watt is his power. His power is 120 watt. Right? Okay. Yeah. A machine gun can fire 10 bullets per minute, each of mass 50 gram. Each of mass 50 gram with velocity 200 meter per second. Find its power. Machine gun is firing 10 bullets per minute with speed 200 meter per second. What
Sir,
is
once can you scroll up?
power? Power is again same thing, work by time. Work by time. Is the machine gun doing any work here? Yes, it is doing work because it is giving kinetic energy to the bullets. Okay, because it is giving kinetic energy to the bullets, it is doing work. So that means, can I write work as kinetic energy?
Complete.
Ke by T. How much is kinetic energy? Half mv
Sir,
square.
change in K na, sir.
B initially 0, so I will take only final. Half mv square. But there are not only a single bullet, 10 bullets are fired. So I'll write here n, some n number of bullets by time t. Okay. So half into mass of each bullet 50. 50 into 10 power minus 3, converting into kg into v square, 200 into 200 into number of bullets 10 divided by time 1 minute 60 seconds. So 0 0 gone, you can simplify it, you will get the value. Okay, in watt, that will be the power of the machine gun. Clear?
Sir, we can simplify half and 50, sir, for now.
Okay, 25 into 200 into 200. Okay, or I'll cancel these zeros. 1 2 3 zeros gone, 10 power minus 3 gone. So it is 20 into 2, 40, 40 into 25. 40 into 25 is how much? 1000.
Thousands.
1000 by 6. 1000 by 6, approximately. How much? 1000 by 6. 100 and how much you get? $166 approximately. 166 watt.
It
Okay.
will be bars, sir.
Right. Right. This is about power. Work, energy, power. This is the end of our syllabus, scheduled syllabus. Okay. All right. So with this, we will be winding up our physics classes for now. And Rajesh sir will tell you the further program. We will be having some further crash course, and of course, next year also will continue the same thing. Students who are in 8 will be coming to 9, and 9 coming into 10. We'll be continuing our classes for them. Along with that, we'll be having foundation classes also. So I hope all of you will be continuing for the next academic year. There are a lot of more details which are to be discussed. Along with the time, we'll go into the further details of each and every chapter. Okay. So it was nice talking to all of you. Nice teaching to you. It was a good experience. So we have some very good, interesting students in the batch, and some, of course, some students are not interacting. I don't know whether how far they are able to follow the subject. We can't assess them because of no interaction. But many students are interacting very good, asking doubts. So it's a happy thing, good thing to know. Right, we'll continue our classes for the next academic year also. See you there.
Thank you, sir. Bye, sir.
Right? Okay, bye and good night.
Bye, sir. Thank you.
Thank you, sir. Bye, sir. Good night, sir.
Thank you, sir. Bye, sir. Good night, sir.